number 42 in standard 408.15 isn't rooted in technical rationale, but rather serves as a placeholder within the standard's history. During the standard's development phase, the authors encountered the necessity of defining the maximum quantity of packets permissible within a single burst transmission. In addressing this requirement, they opted for the number 42. This selection wasn't arbitrary, it was conceived as a temporary numerical value. The rationale behind this specific number was twofold. Firstly, it presented a magnitude deemed sufficient to encompass the prevailing demands of the majority of applications operational during that historical period. Secondly, it deliberately avoided excessive magnitude, thereby precluding any potential impracticalities that might arise from an excessively large numerical constraint. Intriguingly, the selection of the number 42 was further influenced by a pop cultural reference. The authors consciously drew inspiration from the renowned science fiction comedy series The Hitchhiker's Guide to the Galaxy, penned by Douglas Adams. Within the narrative of this series, the number 42 assumes the profound significance of representing the answer to the ultimate question of life, the universe, and everything. The standard's authors integrated this whimsical element as a subtle nod to the literary masterpiece. Their intention was to imbue the standard with a touch of memorability, thus enhancing its recognition among practitioners. The number 42 has undergone a transformation, evolving from a mere placeholder to an inherent component of standard 408.15. It is now recognized as an intrinsic facet of the standard. The standard encompasses various aspects related to data transmission and communication protocols. Understanding the components includes data encapsulation, packet structures, and transmission protocols. Data encapsulation involves packaging data into packets for transmission. This process adds headers and trailers to the data, providing information necessary for routing and error detection. Packet structures define the format and organization of data within a packet. These structures typically include fields for source and destination addresses, sequence numbers, and payload data. Transmission protocols govern the rules and procedures for transmitting data packets across a network. These protocols handle tasks such as error correction, flow control, and retransmission. Consider the maximum packet size limitations. These limits ensure efficient network utilization and prevent fragmentation issues. Factors influencing packet size include network topology, protocol overhead, and application requirements. Standard 408.15 specifies the maximum number of packets that can be transmitted in a single burst, impacting network performance. Burst transmission techniques can enhance data throughput by grouping multiple packets into a single transmission sequence. Considerations for burst transmission include buffer management, error handling, and flow control mechanisms. The choice of the number 42 as a placeholder was influenced by the need to accommodate various application types. Applications with differing data transmission requirements necessitate careful consideration of packet size and burst transmission parameters. Common application types include real-time streaming, file transfer, and interactive communication. In real-time streaming applications, such as video conferencing, low latency and consistent data delivery are essential. File transfer applications, such as FTP, prioritize reliability and error-free transmission over high speed. Interactive communication applications, such as online gaming, require low latency and minimal packet loss to ensure responsiveness. Standard 408.15 addresses error detection and correction mechanisms to ensure data integrity. Cyclic redundancy check (CRC) is a commonly used error detection technique. Forward error correction (FEC) techniques can correct errors without requiring retransmission. Error handling procedures involve detecting, correcting, and reporting errors during data transmission. Flow control mechanisms regulate the rate of data transmission to prevent network congestion. Congestion control algorithms adjust transmission rates based on network conditions. Buffering techniques provide temporary storage for data packets during transmission. Buffer management strategies optimize buffer utilization to prevent overflow and underflow conditions. The impact of packet loss on network performance necessitates robust error handling and flow control mechanisms. Packet loss can degrade application performance, leading to reduced throughput and increased latency. Retransmission protocols retransmit lost packets to ensure reliable data delivery. Quality of service, costs. Mechanisms prioritize network traffic to ensure critical applications receive preferential treatment. Differentiated services, DiffServ, and integrated services, IntServ, are commonly used QoS architectures. Network performance metrics provide insights into network behavior and assist in troubleshooting. Throughput, latency, and packet loss rate are key performance indicators. Network monitoring tools collect and analyze network performance data. Analyzing the evolution of networking standards reveals the iterative nature of technological advancement. Successive generations of networking standards build upon previous versions, incorporating new features and improvements. Backwards compatibility ensures that newer standards can interoperate with older equipment. Future trends in networking include increased bandwidth demands, virtualization, and cloud computing. The architecture of data networks involves interconnected devices and communication protocols. Network topologies, such as star, mesh, and ring, define the physical or logical arrangement of network devices. Routing protocols determine the path that data packets take from source to destination. Switching techniques forward data packets based on destination addresses. The TCP/IP protocol suite is the foundation of modern Internet communication. TCP provides reliable, connection-oriented data transmission. IP handles addressing and routing of data packets. The OSI model provides a conceptual framework for understanding network communication. Each layer in the OSI model performs specific functions such as data encapsulation, error detection, and flow control. Network security protocols protect data from unauthorized access and modification. Firewalls prevent unauthorized network access. Encryption techniques scramble data to protect confidentiality. Authentication mechanisms verify the identity of network users and devices. Wireless networking technologies enable communication without physical cables. Wi-Fi is a widely used wireless networking standard. Bluetooth provides short-range wireless communication between devices. Mobile networking technologies support communication while users are in motion. Cellular networks provide wide-area wireless coverage. Network management tools monitor and control network devices. Configuration management tools automate device configuration tasks. Performance monitoring tools track network performance metrics. Troubleshooting tools diagnose and resolve network problems. The standardization process ensures interoperability between different networking devices and technologies. Standards organizations develop and publish networking standards. Compliance testing verifies that devices meet the requirements of a given standard. Interoperability testing ensures that devices from different vendors can communicate with each other. Future directions in networking include software-defined networking (SDN) and network function virtualization (NFV). SDN separates the control plane from the data plane, enabling centralized network management. NFV virtualizes network functions, allowing them to be deployed on commodity hardware. These technologies offer increased flexibility, scalability, and cost-effectiveness.